And again, it's the stress multiplied by the area. But you need to know this by yourself whether or not your bolt is carrying tension or shear. Because the spec would say use nominal stress. But it's nominal tension or shear, you need to figure that out yourself. Okay? And use the numbers that we just mentioned before. Now, a little bit more about this is that if your bolt carries tension and shear at the same time, because there are two different stresses, we need to have to find a way to combine them, right? Because tension is normal stress, shear stress is shear stress. They are in two different planes, so we need to have a way to combine them. Now, the general idea is just to use the vector approach. That is, you use the stress divided by the available strength that you have, and then use the vector sum. Shear and shear is here, and then tension. The stress that actually occurs, and then the stress that you have as a nominal stress. Then take the square and sum them up. If it's less than 1, it's safe. The funny thing is that you're not going to see these formulas up front. If you look at the spec, what you see is this formula, which I never use, because I don't want to memorize what is multiplied by 1.3. It's confusing. But then again, I think they use this because of the slide rule problem. The slide rule cannot solve this. But somehow they forgot that we already had calculators, right? So they could just use this formula. These two formulas are hidden in the commentary section. And when I read the spec, I love to read commentary. It's kind of fun, as I said yesterday, because it would let us know why we have this kind of formula or how things work, how they bridge the gap between the research and the practice. So for me, I would just use this because it's a stress divided by the strength, very easy to remember and very easy to understand. It should be the same because right here they just try to make this a linear equation by removing the square term and try to change the quadratic function into a linear one. That's why they have 1.3. Kind of crazy, but yeah, So we don't need this one. We can just use the more sensible one because we have calculators. Okay? All right. Now it's time. We now know the strength, we know the nature, we know a little bit about the installation. It's time to talk about the design point of view. Now we need to know the type of the load. The first one is the easiest one, the direct load. When we have the bolt group like this and the force transfer through the centroid of the bolt group, we have a direct load or concentric load. Okay, no problem. The thing is, we can also have one shear plane. When we have two plates, we can have double shear plane when we have more plates, and multiple shear planes when we have much more plates. The thing is that if you have two shear planes like this, for example, if the failure is going to occur with the bolts, both planes will have to fail at the same time. So that means the shear strength of the bolt is doubled. Good, right? So should we have this? No, you need to have a lot of plates and the installation problem may become problematic. So if you have two planes, good. But you win some, you lose some, right? You get more strength, but you have more problem during installation as well. But keep that in mind, you have your strength doubled if you have more planes, okay? And you can have the condition where the load is here. It's not at the centroid of the bolt group, so we have eccentricity problem. And this is a very classic example, right? It's like a corbel structure. And this is the boat under tension, but this case I rather not talk about this today because if your plate here is too thin, it can deform it can help pry the boats out of the support. We have what is called prying action. And now your boat will have to carry both the tension itself and the prying force. So overall, we have less load carrying capacity for the boats. Not good. We can solve this by making the plate thick enough. Okay? And we can have a case like this where your boats may carry tension and shear at the same time, and therefore we need to combine the stress. Use the equation that we previously saw. Okay? Now, if you have the eccentricity problem, we need to mention the eccentricity a little bit because we're going to need to consider this when we design the shear connection for the beams. The load carrying capacity, of course, will have to be reduced because you don't have the pure force acting on the centroid. We use the classical approach, and you know that you need to move this load to act here, right? You remember your days with the subject called statics? I remember it's one of the first things taught. If you don't have the load here, the load will travel here, but instead, you need to apply another force to maintain the equilibrium, and therefore a couple is turned into some kind of a moment or torsion. So yes, apparently if the load is there, it means that your boat group will experience the load itself and extra torsion at the same time. That is why its capacity is reduced. Okay? And yeah, we have two ways to solve this problem. The first is classical method. Does that mean we have to listen to Beethoven before we can start solving this? Well, I hope not. Now, if you prefer Metallica, you can just use Metallica as well. We use classical method, which is based on the vector analysis. Okay, this is a very, old school one from the day of mechanics of materials. We can do that. And another one is called the ultimate strength method. We can also do that if we have time and if we are crazy enough because it's gonna be a very long calculation. But I used to do this when I was taking the class. And I remember when the eccentricity becomes a little bit more complicated, it took me one day to try to solve it, and then it took me one day because I gave up. After one day, just couldn't do it. So no more of that. So, but anyway, the classical method is much easier in terms of the calculation. It gives you the opportunity to do something when you don't have time, when you don't have the means to do complicated calculation. But, being classical, it means that it might not be so accurate. So that is the downside of it. And it gives less strength, and it is not, say, very precise in terms of, the assumption that it uses for the behavior of the boat group. This is, of course, much more precise and predicts the strength better because it has a better assumption. It's just so hard to calculate. Okay? Now, if you use the classical method, it means that you need to move the force to the center of the boat group, and you have this as the bonus, right? Generally, people would call this moment, but the way it creates a force, the extra force on the boat is actually a torsion itself, right? This is torsion because it's going to twist our boat group. So when you have the classical method, you can calculate the force acting on the boat, say, by using this very simple approach. Simply the force divided by the number of boats you have. So now you have this. See, we can use this because of that boat group factor. And then we calculate the force acting on each boat from torsion. Again, this is the basic torsion formula from your old days, right? Tj over, T rho over J, that kind of thing. So the D would be the distance from the centroid to each force here, see it has to be perpendicular. And then the IP here is polar moment of inertia. Basically, this is equal to Ix plus Iy. And the way we calculate Ix and Iy would be simply summing up the moment of inertia of each bolt. Excuse me. This is easy because it's classic, right? If it's classic, you need to be able to do it anytime, anywhere, with a simple calculator. I need to leave something here so that, okay? Let me try to use this once more. All right. Too far away. Now, if you want to calculate the moment of inertia of this bolt group, now IP is going to be equal to Ix plus Iy, right? So that becomes our x-axis. This is, of course, our y-axis. Now, Ix would be equal to the moment of inertia of the bolt itself plus the AD square term, right? That would be the AD square term. Just watch the unit because A is a square centimeter and D square, now you have another square. So that is the unit of moment of inertia. Now, the moment of inertia of this circle itself is pi d to the power of 4 over 64. This is really small. And we can just say this is negligible. You may want to include that in the calculation, but it doesn't matter. It's like if you have a million baht and you find 1 baht on the street, like that kind of feeling. And remember, we approximate things. We don't need exact solution. So that means the moment of inertia in each axis, we can just say it's the summation of AI di square. So if you want that, it's fine. So if you don't want that, it's also fine, right? And for Ix, for this example, would be the summation of the AD square of this, and this bolts. And the Iy would be the summation of all the 6 bolts because the D will become this distance, right? It's pretty simple, really. So now you can have IP very quickly by summing up the Ix and Iy. I don't want to go into that because every time I mention this in the class, I always have fun messing up students with the IP because they should know that if you have, oops, you need this, right? Perhaps. Because they should know that IP or Iz is a constant. It's always equal to Ix plus Iy. So if I rotate the axis, into any x prime or y prime axis, it's going to always give you Iz because of the rules of equilibrium. So Ic is always equal to Ix plus Iy regardless of the axis that you rotate, like that. Okay? So now we have IP. So we can come back here, and this is the true force, right? But if we want to sum up the force, we better change the force into the x and y component by using sine cosine. And the sine term is y over d. D is this moment arm. And cosine is x over d. So if you multiply sine cosine into the equation here, you see that the d term will be cancelled with that one. So you have the force in the x component equal to the torque multiplied by the moment arm in the y direction and divided by IP. And it makes sense because if you have the force in the x component like this, to have torsion you should multiply by the moment arm in y, right? If you have the force in x direction, you should multiply with the moment arm. If you have the force in y direction, you should multiply with the moment arm in x. Otherwise, you cannot cross the vector. All right? And this is we all in this room know that force is a vector. And now they try to teach forces in the primary school, and no students knows vector. How can you teach force without teaching vector? That is beyond me, right? You don't teach direction, then you teach force? Unbelievable. Unbelievable. So that's classic method, okay? Any question on this? We can always use this, right? Whenever we face a problem, we can always use this because it's easy enough, but keep in mind that the results may not be accurate and maybe too conservative as a result. Okay? And keep in mind that the assumption that this classical approach uses is that, see, the rotation will occur about the centroid of the ball group, right? Do you think that is true? No, it's not. Because this would suggest that your plate or your, base structure, whatever that is, must be absolutely rigid, so that the rotation would just occur here. But in the real world, your plate, your base material will also deform, right? So the true movement will occur in this fashion, rather like that. It will rotate about one place, not here. This place is called instantaneous center of rotation. Wow. Yeah. Let's say it's somewhere in the universe. We don't know where, but it's there. So our job is to find that out. And when we have this center of rotation, we can relate how much each ball is moving by, referring back to this point. And when we know how much each ball is moving, we can use that information and plug in this load deformation relationship. So when you know the deformation, you know the load. Sounds scary, right? Because we need to keep using the trial and error until we know where it is. Because if this is the correct point, the calculation from the load deformation relationship will lead us to perfect equilibrium. So imagine if you assume the location here wrong, you will have a wrong deformation and therefore you have the wrong force and you will never have equilibrium. That is why it took me like a day to do it, Anyway, somebody has done this for us. It is all the results of this approach is presented in the design manual, which some of us have, some of us may not have. Okay, if you have the manual, you can just look it up at the table and just take the force out of that table, and all the calculation on the table is based on this approach. Okay, but if you don't have that, we're just gonna have to stick with the classic. That's it for the boats, I suppose. Now it is time for, we're going rather fast today, so the pace is good. Somehow, I don't know. Can't believe it. Now is the whale. Any question about the boats, ladies and gentlemen? Yes. Because, it's a very good question. We need to know that the material that we use for the boat is a high strength material, and therefore it doesn't really have the yield plateau. And that is why. If you see the stress strain relationship of the boat material, it looks like this. Because the strength is so high, so it doesn't yield really. It's a very brittle material. It looks like that. Okay. Any more questions about the boats? Now we go into the welds. So I think there's a wrong notion about using the welds because many people would just prefer the welds to the bowl because they feel like everything is connected, which is quite wrong, you know. If you design the weld incorrectly, it can collapse as well. It doesn't mean that, okay, if everything is welded together just like using a glue and it's going to be safe. No. And right now, you know, the big construction companies, they prefer bolts to welds because of, you know, the quality of the bolts can always be controlled if you buy good ones. You don't have to worry about that. But right now, the quality of the welds will depend on, of course, the welders, right? And right, but welds are good in many ways as well. And I have to say that if you somehow need to transfer a very huge amount of force, you can always use that full penetration weld, right? It's going to be stronger than bolts, of course, but it's going to be more costly as well. Okay, so in terms of the weld itself, we have so many types of weld. If you weld, you know, the bottom of the plate together, this is called the butt weld, end-to-end stuff. If you weld it like this is a typical weld type that we are familiar with. It's a lap joint. If it's like this, then it's a T. We have the H, we have the corner, and we have the plug and slot. Generally, the most commonly used would be the first three, I suppose. This is not a very good idea. Very hard to control. And if you don't really need to do it, please don't use it. That one is also a bit difficult, but it's for the box, right? Maybe. Okay. And the plug and slot would be is similar to using the bolt. You have holes, and then instead of using the bolts, you use the welds instead. Just fill the welds into the holes, and it becomes plug and slot. Okay. So we have full pan, we have partial pan, we have fillet weld, we have tack weld. I hope everybody knows what tack weld is, right? In Thailand, we just call tack, right? So it's English, nah? See, we already use the English, right? Anyway, and then plug and slot for the plug and slot holes, okay? Generally, the position of welding would be the downhand, which is a typical welding process, very easy to control, the horizontal, the vertical, and then the overhead, which is the least preferred method, because the fire will drop onto your head, right? Well, no, it's very hard to control the quality, that's all. Okay, and this is the typical symbol that we use. Please pay attention to the symbol that you use, because if you are good engineers, you can design everything, but you use the wrong symbol, it means that you cannot communicate with welders. So you need to use the right symbol, and there are so many available, I think, in the spec as well. The typical one that we use would be like this. I myself don't remember which triangle is the near side, which is the far side. If I really have to be specific, I need to look at myself as well. And we have the triangle, meaning the near side, the far side, but it always points to the right, you know. No triangle to the left, okay? It's just a universal symbol. So it's always pointing to the right. If you want to weld all around the piece, you just use the circle here. If somehow you need to weld in the field, we use the black flag here, okay? And you can always include extra notes to make sure that the welders understand you by giving the size of the weld, the length of the weld, you know, and the strength, and so on and so forth, okay? It's not a time to just, I'm just going to keep the information to myself because I don't want you to know it. If he doesn't know it, how can he weld correctly, right? So you need to give as much information as possible. And this is a symbol for the full penetration. Okay. Now the welding process. Next, now we have the typical one that we generally use. It's called the shear metal arc welding. I don't know why I don't include the picture here, but I will draw in a moment. This submerged arc welding is done by the machine, and it's generally in the of course, in the factory. I don't suppose we use this a lot in civil engineering work. Now, so we generally use this, and I'll come back to this in a minute. One thing we need to know before is the economy of welding. Now, this is based on, say, foreign economy, because the welders over there earn much more than me. So they don't want to pay a lot to the welders. So they have to always consider the economy of welding. First of all, generally, if you can, the maximum weld size should not be more than 8 or 9 millimeters. That is the maximum possible size for a single pass. That means if you use the 12 millimeter weld size, the welder would have to do it twice to have the weld that big. So it takes more time. They don't like it. So if they can, they would just try to limit the maximum weld size to just 8 or 9 millimeters. That is when the welder can do the single pass and then finish the job. If you use more than that, just 2 passes. Okay? If possible, they would just increase the length of the weld to keep it a simple single pass. All right. And next is the maximum weld size for the fillet weld is about 18 millimeters. If somehow you cannot increase the length, you run out of space to increase the length, and you can still come up with, after the calculation, with the weld size greater than this, it's time to use the full penetration method, because it becomes very, very hard to do. Okay? Now let's go back to this. It's time to draw something. I forgot to. Okay, let's draw it here. Easier. Now the nature of the welding is like this. Say just some plate. When I weld it, it's going to look like this. Oh, actually, more like that, more like a circle. Now, whatever we do, the weld shall always fail here at 45-degree angle. And no matter what the force that the weld carries, the failure here is always weld shear rupture. Always shear rupture. I've done it, believe me. Bang! Just shear rupture of the weld. And it cuts straight through the weld just like that. It's like a knife through the butter. But this is no butter, this is steel. And that is why this is 45 degree, and if that is a T, so your T effective is always T multiplied by sine or cosine 45 degree. And this is 0.707. Or that is 1 over square root 2, right? Let's see the number of one of my car's license plate. I didn't take that number because I was so crazy about the weld, but it's just a coincidence. Anyway, yeah, it's kind of a good idea. Wow, Steel Man used 707 for the license plate. Kind of cool. Anyway, that's it. That's why when you calculate the effective thickness, it's always this. Always. Okay? Now let's move on to what's the break, Kun Tam? 10:30, 10:15, 10:30, and then 11:30. I don't know. It's up to you guys, because I think we're gonna have an early lunch. Say early bird, right? Early lunch. 10:15, right? So we have a not so long first session, right? Just getting warmed up, right? This is it's early Sunday morning. Okay. Oh, we already talked about that, right? Now, it's time to know a little bit about the minimum size of the welds that you should use. Now, when you select the size of the well, the minimum well size would be based on the thinner of the two plates that you join. For example, if you join two plates, one is 6 millimeter thick, another is 20, you base the minimum size of your well on the 6 millimeter, which is the thinner one. And that if it's 6 millimeters, okay, it means a 6 inclusive. Inclusive, it means up to 6, right? Including 6. So between 6 and 20 millimeter plates, the minimum one, the smaller one is 6. So that means the minimum size of the fillet well required would be 3 millimeters. You can use bigger than that, but you cannot use smaller than that. Okay? If it is between 12 millimeter plate and 25 millimeter plate, you're going to have to use 5. If you use smaller than this, you may have the problem with the so-called heat synchronization. And if the heat doesn't synchronize, it means the welding metal, it just doesn't seep into the base metal enough, and therefore your weld may not be strong enough. And the next one is the maximum. Okay, wow. If the plate is not thicker than 6 millimeter, you can use the size of the weld up to the thickness of the plate. If it is thicker than that, you cannot use more than the size of the plate minus 2 millimeters. Again, if you use too big a size of the weld, when the welders do it, it may have a hole behind it. So you cannot use the size of the weld too big as well. Otherwise, it may have a hole like this. I think there's a picture somewhere in the spec as well, which is so big, it may have a hole here. Okay. And next. Again, cannot use too big, cannot use too small, and we cannot use it too long or too short as well. Okay. Here. The minimum length not less than 4 times the nominal size, but I don't think we should worry about this one, because if you use, say, 5 millimeter well, 4 times 5 millimeters, that's only 2 centimeters, right? So has anyone here done the welding before? I know my students haven't. My former students haven't, because they're the new generation. But I used to do it when I was an undergrad student, and you just need to do it like this. And then after, you just got going. It's already 2 centimeters, right? So this is really nothing. Okay? And the maximum size of welding, again, they are worried. It's pretty much the same when we look at the bolt group. If the weld is too long, how can you be sure that at the beginning of the weld and at the end of the weld, the stress is equal? Because make no mistakes, ladies and gentlemen, if I'm to draw another picture, let's say if I weld it like this, apply tension like that, what do you think the stress on the weld would look like? You think it's going to be uniform like that? No, sir, it's not possible. The true stress should look like this. But do we care to calculate this? No, sir. we don't care as well. We're just going to try to find a way to, I'm fine with this. Right? See, we use scientific method. We're not scientists. You ask a scientist to design the well, they will be busy trying to integrate this stress. Right? And we just, I'm done. I'm just going to go home. Have a cup of coffee before, watching movie. And they just, we need to find the function of that line and then integrate that sort of thing. So we live in a world of approximation, right? That's why we need statistics. So yeah, that's a problem. So when it becomes too long, we need to be a little bit concerned about that as well. And yeah, they got the formula for the reduction factor that you will see from the slide. But you know what? I also struggle to believe that formula because I did some tests on the wells and my wells would fail long before the value suggested by this formula. So keep that in mind because again, well is quite a brittle material, and because you asked, the stress-strain relationship of the well itself is pretty similar to that of the boats. There's no yielding, but it has yielding value. It just goes by very quickly. Okay, so we have that, and end loaded would be just like the picture that I just drew. We have the welds on the end of the member, and that becomes the end loaded stuff or end loaded connection. Okay, and this here can be calculated based on the length of the well, and W would mean the distance between the well, or from the picture, the width of the plate. So let me go back to the picture again just to help clarify this nomenclature. This should be W, and that should be L. Okay. All right. Any question, ladies and gentlemen? Crystal clear. Connection is very simple. I don't do hard stuff. I only do simple stuff. Okay. That's it. Now, comes down to the strength. Okay. As I mentioned before, no matter what the types of force that the well has to carry, it always fail here under well shear rupture. So the strength of the well will be simply equal to, let's say, use the ASD, 0.6, that's 1 meters, multiplied by the ultimate strength of the well. And it's pretty easy to memorize here. If it's E60, that's a 60 kip per square foot unit. Multiply by 70, you get kilogram per square centimeter. So if it's E60, it's 4,200 kilogram per square centimeter. Multiply by 0.6, you get the shear. And then multiply by 1 over square root 2, right? And then the size of the well to obtain the effective thickness.